Yes. Now, can you give me examples of conductors? Examples of conductors. Martin.
It's metals.
Come again.
Metals.
All metals are conductors. So all metals are conductors. Can we explain why? What do metals have? What does special properties possessed by metals which makes them suitable to be used as conductors? What are these special properties?
Metals have delocalized electrons.
Daniel, what do you mean by they have delocalized electrons?
Electrons that are freely moving.
Electrons that are freely moving. So all metals have electrons that are freely moving. Okay, it's true, it's true. But can somebody still explain it further? What do we mean by metals that are freely moving? Can somebody give a detailed or further?
They have low ionization energy.
Hey, Ray, Daniel, you are taking me into the world of chemistry. Okay, go ahead. And if they have low ionization energy, okay, let me take over. Daniel, all that you are saying is true, but I want us to understand it practically. You see, if you look at all metals, example, sodium, magnesium, sodium, magnesium, examples of metals.
Aluminium.
Aluminium,
Titanium.
Titanium, copper, iron. You see, all these metals have few electrons in their valence shells. So if we look at the electronic configuration, let me use the JHS electronic configuration. So these are the shells. Let's take sodium, for instance. Sodium has 11 protons in the nucleus. Within the shells, these electrons are even distributed, 2 here, 8 in the L shell. Then we have 1 in the K shell. If we look at magnesium, with atomic number, what's the atomic number of magnesium?
12.
12. If we look at the distribution, plus 12 protons, 2 here, 8 here, and then 2 in the last shell. This last shell is known as the valence shell. Valence shell. And the electrons within the valence shell are known as valence electrons. So all metals, group 1, group 2, and group 1 and 2 are metals. Good. So what it means is that the proton must actually impose nuclear attraction on the electrons within the shells. But because we have lots of electrons within the inner shell, look at this is KLM. Look at the L shell. We have lots of electrons within the L shell than the M shell. So we said that the inner shell, the innermost shells are fully filled. So what happens is that the protons or the nucleus imposes attraction because the nucleus is positively charged, electrons are negatively charged. The nucleus must attract the electrons in the shells. But because of this inner filled shell, it reduces the attraction on the valence shell electrons. So this electron in the last shell is not so much attracted to the nucleus because of this numerous electrons within the inner shell. So they tend to shield. They shield the nuclear attraction on the valence electron. Please, are you following the discussion?
Yes.
Are you following?
Again. Yes.
So the inner filled electrons shield the nuclear attraction from the valence electrons. So this one that must be attracted by the nucleus is shielded by the inner electrons. And because of that, that electrostatic force of attraction on the last shell, the valence shell, the valence electron is less. It's less. Once the attraction on this valence electron or last electron is less, it makes these electrons to be free. Okay, because of lesser nuclear attraction, okay, shielded by the inner electrons, this last electron, known as the valence electrons, are, because they are less attracted to the nucleus, we say that they are free. If they are free, then they can easily move about. Daniel, that is why you said electrons have free and mobile electrons, valence electrons.
Yes.
They are free because of the less nuclear attraction. They are mobile because once they are free, they can move about within the shell. And all metals have this special property. Metals have free and mobile valence electrons. And this property makes them suitable to be used for electricity. In creation of electricity, the valence electrons must just be moved to move into another energy level. And once they are able to move freely, that is the reason why metals are suitable. All metals are conductors, meaning they can conduct electricity and heat. Conductivity. Thermal conductivity is by the flow of electrons. Okay. Electric conductivity is also about the flow of electrons. So this is that special property which makes metals good conductors. They have free and mobile electrons, valence electrons. Please, is there any question? Is there any question here? All right. Frank.
So what makes the valence electrons of non-metals like not free?
Good. So if you take non-metal, like let's take nitrogen, for instance. If you draw the electronic configuration, we have 2, 5. Give me another non-metal.
Okay.
Oxygen. Oxygen, for instance, with atomic number. What's the atomic number of oxygen?
8.
2, 6. We have, so KL shell. We have lots of electrons in the valence shell. Okay. And so because of these few electrons in the K shell, but more electrons in the last shell or the valence shell. So it makes the attraction, the nuclear attraction, even. The nuclear attraction or the protons that must attract the electrons are evenly distributed. Unlike these ones where we have lots of inner filled electrons which actually shield the valence electrons. So here, Frank, in non-metals, the nuclear attraction is evenly distributed on the electrons. Frank, are you okay?
Yes, sir.
Whereas here, we have the inner ones shield the few valence electrons in the valence shell as well. All right. Now, another property, conductors have this. I think let's go into it a bit deeper. What special property do conductors have? Why are they conductors? We have what we call energy band theory. Energy band theory. You will be doing this later in electronics, but let me take the opportunity to explain a little bit. Energy band theory. In energy band theory, we have what we call the valence band and then the conduction band. We have energy levels known as the valence band, and we also have what we call conduction band. Now, what do we mean by valence band? You see, the structure of a material is by the covalent bonding of individual atoms. So if we take aluminum, we have aluminum atom, one aluminum atom bonded with another aluminum atom, okay, a lot of individual atoms come together to form that complex structure. So if you pick small aluminum, we have individual aluminum atoms coming together to be bonded covalently to form the structure of aluminum. And in bonding, it is the valence electrons that are used for bonding. So if you pick sodium for instance, one sodium atom has a single electron in a valence shell. Another sodium atom also has a single electron. So these two electrons, okay, come together to obey the doublet rule. So another sodium atom, one single valence electron, another. This is how the structure is formed. So the giant material sodium you see is due to the bonding, the covalent bonding of sodium atoms in order to form this giant structure. And so, Ernest, quickly.
Okay, so say, can we say metals are magnets? Magnets are conductors.
No. Magnets, you cannot say that are directly conductors. Yes, we know iron, okay, iron is a magnetic material. The explanation to magnetism is not the same as electricity. So let me explain this. When we get there, you understand why the same metals, iron is a magnetic material, aluminum is not. Is that okay?
Yes, sir.
So the giant structure of sodium is due to the covalent bonding of the valence electrons and shells of sodium. Now in bonding, it is the electrons in the last shell, the valence, that are used for bonding. So electrons in the valence shells or last shells are used for bonding. So when you have an atom of a material, another atom of a material coming together to be bonded covalently, okay, they're coming together of the individual last shell and electrons of atoms constitute what we call valence band. So when we talk about valence band or valence energy level, it is basically the bonding of the valence atoms of same materials that come together to be bonded covalently. Okay, so the same atoms, your last shell, my last electron, your last shell, individual atoms will come together to be bonded covalently, and they constitute what we call valence band. Please, you understand? Hello, do you understand? So that is how the valence band or energy level is formed. So always, I'll explain. Always, the valence band, we say that it is always fully filled with electrons. Why is the valence band or energy level fully filled? Because it is the individual valence electrons that come together to be bonded covalently to form the valence band. So if one sodium atom will bring its last electron and then bond it with another sodium atom. So this sodium atom would also bring its last electron. Another sodium atom will bring its last to be bonded covalently. And this is what forms the giant structure of sodium, aluminium, iron. Okay, so because this valence band is as a result of the bonding of the valence shells and electrons, we say that the valence band is always fully filled with electrons. Now from the valence band, the next band to talk about is the conduction band. Okay, conduction band. So let's draw lines. So for a particular material, this is the valence band. What we have in the valence band, the valence band is always fully filled with electrons. Why? Because it is the valence shells of different atoms that come together to form this. So we always have electrons within the valence band, fully filled. The next band is the conduction band. When electrons manage to move from the valence band into the conduction band, we say the material is electrically conductive. So when electrons manage to move here and come to into the conduction band, the electrons are free to move about from one atom to another atom. That is when we say that the material is electrically conductive. Now, in conductors, the distance or the space between the valence band and then the conduction band is very, very small. So in conductors, if the valence band is here, you have the conduction band also here. Just small space, or sometimes we say that in conductors, the valence band and then the conduction band overlap. They overlap. Overlap is similar to two people crossing their hands. Okay, so Augustine crossing your hand with another person. Okay, it means we have overlapped our hands. So in conductors, the valence band and then the conduction band overlap. If they overlap, it means there is almost small space or no space between them. So at even 0K, at 0K, because the conduction band and then the valence band overlap, electrons can easily, I'm coming in. Electrons can easily move from the valence band, which is a hub of electrons, into the conduction band. So electrons are here. Because of that small distance or the overlap, electrons can easily move into the conduction band. Easily. Okay. So in conductors, at ordinary temperatures, there is some level of electrons within the conduction band. And this is due to the overlap. Now, when you increase temperature of conductors, more electrons can migrate from the valence band into the conduction band. But when the temperature is so much, electrons in the conduction band can get saturated. There will be so many that their movements can be restricted. Okay, and this is the reason why we say that for conductors, when you increase temperature, resistance also increases. Resistance increasing means that the electrons cannot be able to move freely, and this is due to saturation in the conduction band. So conductors can actually conduct because there is the valence band and then the conduction band overlap. And so at ordinary temperatures, which is 0 Kelvin, the electrons can freely move from the valence band into the conduction band. Please, if you have any question, quickly ask before I continue. Is there any question? Yes, Gideon.
It means at high temperature. It means at high temperature, a normal metal cannot be able to conduct electricity.
Well, yes, the conductivity will reduce. When you increase temperature, conductivity of electrons would reduce because of saturation of electrons within the conduction band. Yes, Martin.
Simply so when the instances occur and then it's moving, it's only the valence electron that moves into the
Conduction band, yes. So
the rest are remained the cells.
come again.
The rest are like kept in the cells, but the
No,
free one
no,
don't.
what I'm saying is that the structure of a material is due to the covalent bonding of the valence shell and then the valence electrons. So to form the structure, it is the valence band and electrons that must come together to be bonded covalently. So any bonding is done using valence shells and electrons. That's what I'm saying.
Yes, please. Thank you.
All right. Then let's look at insulators. And why would they be insulators forever? Yes, if I ask you what an insulator is, you'll be able to tell me. So Anna, what is an insulator? Anna.
If an insulator is a material that has a high electrical resistivity, electrical conductivity.
Okay, thank you. Or can somebody also define insulators in a different way? So Anna is saying that insulators have a very high, okay, Ernest. Ernest, go ahead. Oh,
Insulators
NS.
are
Mhm. Yes, I'm listening to you.
Sir,
I'm listening.
conductors are materials that restrict electric current or heat to flow through them easily because they have limited moving electrons.
We are talking about insulators. Oh, I
Sorry.
heard conductors.
Sorry. Insulators are material that restrict electric currents or heat to flow through them easily because they have little to none moving electrons.
Okay. All right. So basically, all that we are saying is that insulators do not allow electrons nor heat to pass through them. That's
Yes, sir.
okay. And why do they prevent this? Because they have a very high resistance. And if we talk about insulators, you can mention a lot. If you are here and then you cannot give me about 10 insulators, then you are not here. So we are not going to talk about insulators. So insulators have a very high resistance to the extent that they do not allow flow of electrons nor heat. So they have a very high thermal and electrical, they have a very high resistance to the point that they resist entirely flow of electrons within them. Now, let's go into the energy band theory and understand why insulators also behave as such. So every material, whether insulators, conductors, or semiconductors, Daniel,
Sir, please, the energy band theory was proposed by who?
by physicists, okay? So it's a theory put together by various individuals in physics. And no single individual is credited with that. So by physicists. So every material has the structure of every material is by the covalent bonding of its valence shells and valence electrons. So when the valence shells and electrons of individual atoms, okay, of the same element come together, they form the structure. So when the valence electrons and shells come together, they constitute the valence band or valence energy level. So supposing this is an insulator, let's use this line to represent the valence band. And don't forget, the valence band is always fully filled with electrons because it is this valence shells of individual atoms of the same element that come together to form this. So it is fully filled with electrons. Now the next energy level is the conduction band or conduction energy level. Unfortunately for insulators, there is a wider gap between the valence band and the conduction band. So if this is the valence band, there is a wider gap or distance between the valence band and then the conduction band. Jackson.
That distance was referred to, say,
Mhm.
I think the distance between the band, the conduction band, is referred to as the forbidden gap.
Yes, I will explain why. So there is a wider gap or distance between the valence band and then the conduction band. And this is known as just as Jackson said, the forbidden gap.
So please, why is it called the forbidden gap?
Because it cannot be overcome. Electrons cannot overcome it. So that space is forbidden. For insulators, that space is forbidden, okay, for electrons. So this wider space is known as a forbidden gap.
Sir, please, what makes it forbidden gap?
Oh, forbidden because no, Daniel, how do you understand the word? How do you understand the word forbidden? In English, how do you understand the word forbidden?
Disallowed.
No. Forbidden.
Yeah, like you're not allowed to.
It's not allowed. Okay. You see, so it is forbidden gap because of its proximity, the proximity between the valence band and conduction band. Electrons are forbidden to cross, and they cannot even cross. They can't cross. So to electrons, this gap is forbidden. So because of that wider forbidden gap between the valence band and conduction band, no matter how much you increase temperature, electrons cannot get that energy to cross this gap. And so electrons would forever remain electrons. You see, they will become insulators when electrons in the valence band can manage to move from the valence band into the conduction band. But because they cannot, they will forever remain insulators, no matter how much you increase temperature of the material. So in energy band theory, there is a wider gap between the valence band and the conduction band, even to the extent that electrons cannot cross, no matter how much we increase or raise the temperature of the material. You can decide to raise it, increase the temperature, or use strong electric or magnetic field. But if you continue increasing temperature, the whole material will just bend for you. That is why you can heat, if you decide to heat metal, wood, plastic, they cannot still become conductors or conduct heat or electricity. And when you increase the temperature so much, they will be bent and then leave you. Please, is there any question? Ask questions if you don't understand something, please. Okay, so let's look at semiconductors. 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 So what is a semiconductor? Daisy, today I've come to you. Daisy, I'm at your home. Hey, Daisy is not around. Yes, class, what is a semiconductor? Anybody? Martin.
Simply they partially allow the flow electric current, but
They
partially allow the flow.
So they partially allow flow of what?
Electric
Charges. Or
Charges.
electric, yes, the flow of charges in them. Can you give me 2 examples? So please, before the examples, semiconductors are materials that partially allow the flow of electrons or charges through them. Another definition can also be that they are materials whose electrical conductivity or electrical resistivity lies between a conductor and an insulator. They are materials whose electrical conductivity or resistivity lies between conductivity or resistivity lies between that of a conductor and an insulator. Can you give me some examples of semiconductors? Examples of, oh, the ladies, you are not talking today. What's your secret? Frempoma, Anna has just spoken. Anita to Nanakumi, you are here. Ashima, you are here. Okay, Martin.
Sir, please, silicon.
Michelle, you're also here. Okay, so silicon, Michelle.
Germanium.
Germanium. More examples.
Arsenic.
Arsenic. So silicon, germanium, arsenic, they are the group 4 elements, the metalloids. Arsenic. They are the group 4 elements, please. So you are chemistry students, so please master them. Okay. So these are metals that will partially conduct heat, electricity with increased temperature, meaning when you increase the temperature of the material or use strong electric and magnetic field, then they would conduct. But if you use temperature and you haven't yet gotten to that threshold, it will not mine you. It will not mine you. Practically, this is it. Let's look at a circuit, a simple electric circuit. This is a bulb. NS.
Sir, please, can gallium be considered a semiconductor?
Yes. Yes. Supposing this is silicon. Every circuit, there must be a source of EMF. So this is our source of EMF. Let's incorporate a key. A key. Or a switch. So if I close this key, for pure wires, for pure conductors, if this is not here, supposing we have a complete circuit, these are wires, conductors. When you close the key, you see the bulb coming on. It will switch It will come on instantly and will go off instantly when you open the key. But for the same arrangement, when we incorporate a silicon, a piece of silicon rod in this circuit, meaning we take out this, the wire. We've just joined the wire with the silicon. When silicon is in place, if you close the key, it will not mind you. Now, if you decide to heat this, expose this to increased temperature, as you heat it, there will be a certain amount of temperature, or at a certain amount of temperature, you see this bulb coming on. It will begin to glow. It will begin to glow. Now, when the heat applied is taken off, then the bulb would go off, meaning this silicon material connected in between would only allow electric charges or charges to flow when temperature is increased. Another way of causing conductivity, so we can cause conductivity of silicon by applying heat with temperature or strong electric or magnetic field. So with silicon, when temperature is increased, conductivity is also increased. But with conductors, when you increase temperature, conductivity is decreased. Please, is that okay?
Yes, please.
Is there any question?
Sir, please, can
Frank.
you go back?
So I'm just creating a circuit. I just have a circuit with a silicon or a semiconductor material. Before what I was doing is that we had a circuit without silicon. So just complete conductors. If there is a source of EMF, when you on it, quickly, when you close the key, the bulb would come on. When you off it, open the key, it will go off. But when you incorporate a semiconductor material such as silicon in a circuit, what will happen is that for this to allow charges to flow, there must be a source of heat. It must be heated. Okay, so as you heat, there will be a certain amount of temperature which will just allow heat, the electrons or the charges to flow through the circuit. So when you get to that temperature, then the bulb will begin to glow until that temperature is reached. It will not glow. Okay, so what I'm saying is that with semiconductors, when temperature is increased, conductivity is also increased. When temperature is increased, conductivity increases and resistivity decreases. Resistivity decreases on the other hand. That is with semiconductors. Then with conductors, when temperature increases, conductivity decreases. With conductors, when temperature increases, conductivity decreases. That's the opposite of what happens in semiconductors. All right. Then let's look at the energy band theory of semiconductors. So in conductors, the valence band and then the conduction band overlap. And so at ordinary temperatures, electrons can freely move into the conduction band. With insulators, there is a wider gap between the conduction band and the valence band, and this gap is known as the forbidden gap. With semiconductors, there is a narrow gap between the valence band. There is a narrow gap very small gap between the valence band and the conduction band. And don't forget, whether conductors, semiconductors, or insulators, the valence band is always fully filled with electrons. Fully filled with electrons. Now, at ordinary temperature, even though the gap is narrow, at ordinary temperatures, electrons cannot move into the conduction band. So at 0K, electrons cannot have that energy to make the jump. Anita, are you with me? But when you increase temperature, electrons in the valence band can obtain that external energy, thermal energy, to move from the valence band and occupy the conduction band. Okay, so meaning that at 0K for semiconductors, at 0K there will be no electrons in the conduction band. Class, are you there?
Yes, sir.
But at increased temperature, because of the smaller gap between them, electrons can get that energy, thermal energy, to move, or magnetic energy to move into the conduction band. That is how come semiconductors will conduct with temperature. Basically due to the narrow gap between the valence band and the conduction band. So these are the details you must understand as disciples of physics. Please, is there any question? Is there any question? Martin, Ernest, yeah, Frank.
Sir, please can you explain conduction band in the valence band?
Frank, speak up.
Sir, please, I'm asking if you can explain the conduction band like the theory for semiconductors in the valence.
Okay, so conduction band is such that when electrons find themselves in a conduction band or energy level, they can freely move about from one atom to other atoms. So when electrons migrate into the conduction band, they can easily move from one atom to neighboring atoms. And conductivity is all about electrons or charges moving from one atom to other atoms. Okay, so when electrons get into the conduction band, they are freely mobile. They can move from atom to atom. And when they do that, we say that the material is being conductive. Now, for semiconductors, they are semiconductors because they can conduct on condition. And what's that condition? When there is heat, when there is increased heat or strong electric or magnetic field. So for semiconductors, there is a narrow gap between the valence band, which is always fully filled with electrons. So the valence band has no issues with electrons, presence of electrons. It is always fully filled with electrons. And I've explained to you the reason behind it. So we have the valence band or energy level, and then the conduction band. Unfortunately for semiconductors, this space between them is narrower. So this is a conduction band of semiconductors. Blessing, are you there? Janelle?
Sir.
Okay. With your sister?
No. Sir, please, I'm here.
Okay. So because of this narrow gap, when you hit the material, electrons within the valence band can easily move into the conduction band. That is why semiconductors will conduct on condition that there is heat or strong electric and magnetic field, meaning they can acquire external energy to move into the conduction band. And once they find themselves within the conduction band, it's hooray, we have come. Then they can move about within the crystal structure of the material. And when they do that, we say the material is conductive. Frank, are you okay?
Yes, please.
Okay. All right. Please, have you exhausted your questions? Have we? All right. Then Ashima. Ashima.
Yes, sir.
What special properties do conductors have which actually makes them suitable to be used as conductors? What special property do metals. Let me use metals have, which makes them suitable to be used as conductors. What do metals have which makes them suitable to be used as conductors? Maybe she missed that connection. Blessing. What do metals have which makes them suitable to be used as conductors?
Sir, please, it's because they have free electrons.
Use free and what? Free and mobile electrons. Okay. Blessing, okay?
Okay, sir.
Then the next question to the class is, using energy band theory, distinguish between conductors, insulators, and semiconductors. Using energy band theory, distinguish between conductors, insulators, and semiconductors. Yes. Yes, who would start for us? Using energy band theory, distinguish between conductors, insulators, and semiconductors. Anybody? Gideon.
Sir, please, using
When you take conductors, the valence band and the conduction band, they overlap, which make the free free moving electrons, like it allows the free moving electrons to easily get into the conduction band, which makes it more conductive. That's for the conductors. And then for the for the insulators, they have a wide gap between their conduction band and the valence band. So when they, like, the gap there doesn't allow the electrons from the valence band to easily get into the conduction band. And then when the exception is added, the exception of the increasing temperature, the gap still doesn't allow for the electrons to be able to cross to the conduction band because the gap is very wide. And then when you take semiconductors, the gap between the conduction band and the valence band is not too wide.
Narrow.
It's narrow. The gap there is narrow. So when, although the gap is narrow, naturally at 0 Kelvin, electrons cannot cross to the conduction band. But then when the semiconductor is heated, which allows the electrons to move faster, the electrons are able to cross into the conduction
Now
band
a follow-up
because
question to the class. Why is it that at 0 K, why is it that at 0 K electrons cannot move into the conduction band? Frank.
Electron
Frank, I'm listening. . .
. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . .
Oh, Frank. Maybe his connection has dropped.
Please.
Ernest.
Sir,
I'm listening.
the reason why electrons cannot move at 0 K into the energy band is because there's no thermal energy to excite them, or let me put it, reactivate them to move into the band, across the band gap.
Okay, Stanley wants to also talk. Stanley.
Okay, so 0 Kelvin is basic. Say please, I think I've done this.
No, we've done this. That's why I'm asking. What happens at 0 K?
Okay, so the molecules, the electrons will possess less kinetic energy and will therefore not be able to
Zero kinetic energy. Okay, so there wouldn't be any activity of the, and don't forget, temperature is directly proportional to average kinetic energy. So if we are 0 K, then there wouldn't be any kinetic energy of the molecules at that temperature. Then don't forget, electrons must also move. All right. So the second question, using energy band theory, distinguish between, is just using the energy band theory of which spells out the gap difference between the valence band and then the conduction band. So you look at it for conductors, insulators, and semiconductors, just as Gideon was saying. So the energy band theory, okay, distinguishing this is that conductors have, and now for conductors, the valence band and then the conduction band actually overlap. Then insulators, there is a wider gap between the valence band and then the conduction band. Then for semiconductors, there's a narrow gap between the valence band and then so this you can put that into writing and also use diagram, just as I illustrated in distinguishing between them, and you get the full marks. That's all. So that's it with conductors, insulators, and semiconductors. Let's look at the energy model, the atomic models, because I also have that in your scheme of work. The models of the atom, atomic models. The atomic models actually spells out how over the years scientists perceived the atom to be. As a disciple of physics, if you are asked to draw and explain how an atom looks like, I don't think you draw anything square, that an atom is a square with balls of Kenke within. No, nobody will do at this level. I doubt if you will do this, because you have gone through JHS where you've been given a picture of the atom and all that. And I'm sure by now your chemistry lesson has also given you a picture of how an atom looks like. Class, is that right?
Yes.
So the models of the atom we have over the years were actually put together or proposed by some scientists. Okay. Now the first possible model of the atom was given by J.J. Thomson, Joseph John Thomson. So J.J. Thomson gave us the first model of the atom, how an atom mass or is seen to be. Then over the years, some other scientists came to propose their own structure of the atom. The second was proposed by Ernest Rutherford. So Rutherford also proposed his atomic structure, then followed by, over the years, Niels Bohr and Dalton. Okay, but in physics, we limit ourselves to Thomson's model of the atom, then Rutherford's model, then we look at Bohr's model. Bohr's model of the atom. In physics, we don't look at what Dalton said and all that. We only limit ourselves to these three models of the atom. So let's begin with J.J. Thomson's model of the atom. How did he model or propose his atomic structure? J.J. Thomson's model of the atom says that an atom is a spherical structure. It's a sphere with evenly distribution of negative charges within the sphere. So he proposed that the atom looks like this, with an evenly distribution of negative charges within the sphere. Then he also went further to say that within the sphere, where we have the evenly distribution of negative charges, we also have positive charges also evenly interspersed or distributed within the negative charges. So all that he was saying is that an atom is made up of negative and positive charges evenly distributed within the sphere. Hello, Frank.
Sir, please. So the negative charges are on the sphere. What we learned in chemistry is that like the positive charges are on like the sphere itself, and the negative charges are evenly distributed. So
no, you see, no, we are not drawing a 3D sphere, just a circle, and within the circle, which is actually a 2D version of how a sphere looks like, we have evenly distribution of negative charges, and within the negative charges are equally evenly distribution of positive charges as well. Okay. This model, J.J. Thomson's model of the atom, is termed as the plum pudding model. The plum pudding model of the atom. The plum pudding model. So if you hear the plum pudding model of the atom, it refers to J.J. Thomson's model of the atom, which says that an atom is made up of it's a spherical ball with evenly distribution of negative charges and evenly distribution of positive charges within the negative charges. Now, in every atomic model, we look at the strength and then the weaknesses of the model. So let's look at the strength and weaknesses of J.J. Thomson's model. Now, what is the first strength that can be extracted from Thomson's model? Can you share with me some of the strength of J.J. Thomson's model of the atom? And I'm saying this because you are chemistry students. Hello? What are the strengths of J.J. Thomson's model? Frank?
His model proved the presence of negatively charged particles in an atom.
Thank you. So, his model made us understand that an atom actually has charges within. From his model, we can say that an atom has a spherical structure. Okay, an atom has a spherical structure, and that is how come when we are drawing atom, we don't draw it as a square or a cone, but it is circular. And two, an atom is made up of charges. It's made up of because he said that there are evenly distribution of negative charges, and within the negative charges are evenly distribution of positive charges. So it means an atom is made up of charges. 3. Michelle, are you there? Hello, Michelle. Oh. What is the third strength? What is the third strength, or what extractions can you make out of Thomson's model of the atom? Anita, can you share something with me? Okay, I think Frank. Frank is ready to share. Okay, Frank.
He was able to prove that atoms are electrically neutral since the protons and electrons are even in the structure.
Exactly. So by his model, he was able to prove the neutrality of the atom. So the other strength is that he proved the neutrality of the atom. Because if we have evenly distribution of negative and positive charges, then they will cancel one another and eventually remain neutral. So J.J. Thomson's model proved the neutrality of the atom. Please, is there any more strength?
Please, the introduction of subatomic particles.
Did he talk about subatomic particles, Joshua? Did he talk about subatomic particles?
Yeah, because
I'm listening.
Because Thomson's model was the first to explain that atoms are not invisible, but they are made up of smaller subatomic particles.
No, Thomson did not give us an idea of the presence of subatomic particles. It was later. Okay. So after Thomson, Ernest Rutherford, who was a student of Thomson, also studied Thomson's model conducted an experiment known as the alpha scattering experiment, and as a result came out with his own version of the model of an atom. Class, are you there? So let's look at Rutherford's model. Rutherford's model of the atom. He proposed his model by using an experiment, by conducting an experiment known as the alpha scattering experiment. Conducting the alpha scattering experiment. Please, if you have an idea of or about the alpha scattering experiment, can you share with me? Because you are a chemistry student, that is why. Okay, Frank, what did he do in his experiment? Yes.
He shot some alpha particles through a gold foil and expected like it to be partly like deflected, but in his observation, the particles were widely like deflected and some reflected backwards instead of.
Okay. Ernest, we are learning, and share with us what you also know about Rutherford's alpha scattering experiment.
His experiment was described as an atom having a tiny, dense, positively charged nucleus at its center, which contains most of the atom's mass.
But I'm talking about the what did he do in the alpha scattering experiment?
Oh,
you are giving me the conclusion.
Oh, then Frank said everything for me.
Okay, so just as Frank said, he had in the material for the experiment, he had a radioisotope. A radioisotope is any material which can emit radiations. Okay, so he used radioisotope which could emit alpha particles. So this is the radioisotope. Please, the ladies, are you there? Anita, Frimpoma, Ashima, and the rest of you, are you there?
Yes, sir.
So this is the radioisotope kept in lead shell. And it is kept in a lead shell because it's radioactive. Later, you go through radioactivity and you understand this thing. Then, this is gold leaf or gold foil. A thin sheet of metal coated with gold. So this is the gold leaf or gold foil. Now, you see the radioisotope emits alpha particles. So these are the alpha particles. Then it was studied under a strong microscope. The whole observation was studied under strong microscope. So what he observed was that about 99+% of the alpha particles could pass through the gold foil without any deflection. So in his experiment, there are observations and there are also conclusions. His first observation was that a larger percentage of the alpha particles pass through the gold foil undeflected, meaning this could just go through this without any deflection. They could just go through it. Then he also observed that about 1 out of 20,000, this is 1 out of 2,000, it was the last one. 1 out of 2,000 alpha particles, and calculate this percentage. Very, very small. Very 0.001 out of 2,000 alpha particles were deflected at angles ranging from 0 to 180 degrees. Meaning, very, very small percentage of the alpha particles were deflected at wider angle from 0 to 180. Then about 1 out of 20,000, very, 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 very small alpha particles were deflected back along the same path. 1 out of 20,000 alpha particles, these particles were deflected back along the same path as they came. Okay, so these were the 3 main observations made by Rutherford. So one, a larger percentage of the alpha particles went through the gold foil undeflected. Then about 1 out of 2,000 alpha particles were deflected along angles ranging from 0 to 180 degrees. Then about 1 out of 20,000 alpha particles were deflected back along the same path. Please, these are the key observations you must understand in Rutherford's experiment. Then, out of his observation, he made conclusions, or he drew inferences. So let's look at the conclusions. So, how did he conclude? What was Rutherford's first conclusion? Yes. What was his first conclusion based on his observation? Anybody? Ernest? Okay, Gideon.
So his conclusion was an atom is made up of a small positive Bain center.
Note that he concluded based on his observation. So you take the first observation and look at how the conclusion he made from that observation. Yasmin, you have been quiet all along.
So, because of the space inside, because the particles passed through inside, that means that there was a lot of space in the atom.
So an atom, thank you. So based on the first observation that about 99% of the alpha particles went through the gold foil undeflected, Rutherford concluded that an atom is made up of a hollow space or hollow sphere. Okay, the structure is basically hollow. Okay, so from the first observation, he concluded that an atom is made up of a hollow sphere, or it's a hollow spherical something. Then, what is the second observation, conclusion? The second conclusion. Let's base our conclusion on the observation. Ernest, your hand was up earlier on.
So I was going to say that atoms have his conclusion was atoms have a tiny, dense, positively charged nucleus at its center, which contains the atom's mass.
We'll come to that. Let's hear from Stanley.
Please since the particles were deflected directly backwards, this showed that he made a conclusion that the atom has a small dense positive center, which the particles made head-on collision with.
Okay, so just as Ernest said, yes. So from his third observation, that 1 out of 20,000 alpha particles were deflected back. Let me hear from Ernest, and then Ernest.
So he also denoted that most of the atoms is an empty space. That explains why most of the alpha particles went straight through.
Oh yes, the empty space one was his first observation, that a greater percentage would pass through without any deflection. Okay, so if 1 out of 20,000 alpha particles were deflected back along the same path, then it means that the atom has something which must have a positive charge, because that thing must have a positive charge. One, that thing must have mass greater than the mass of the alpha particles. And so the third observation spoke about the presence of the nucleus. Okay, there is something at the center which when the alpha particles collide could deflect them back along that same path. That thing must also have a greater mass than the alpha particles, and it must also have a charge, okay, which is the same as the mass of the alpha particles. And then the third observation, conclusion he made, based on 1 out of 2,000 alpha particles were deflected at angles ranging from, also explains the presence of the electrons within the sphere, because you see, though the atom is made up of empty space, but we never had a situation where all the alpha particles were able to pass through. Some were deflected, meaning there is something within the empty space which could deflect alpha particles at the angle ranging from 0 to 180, and so explain the presence of the electrons within the sphere. And the third one talks about the presence of the central core, which is the nucleus. The nucleus being positively charged, and the nucleus having a mass greater than the mass of the alpha particles. So these were observations made from his, the conclusions drawn from his observations. Please, is there any question? So let's quickly move on to strength. What are some of the advantages or strength of Rutherford's model of the atom? What are the strengths? The strength of Rutherford's model of the atom. Please, these are the basic stuff you must know. Yasmin, break your eyes for us. Can you tell us about one of the strengths of Rutherford's model of the atom?
He was able to come up with the fact that there's a presence of nucleus.
Thank you. It's because before, Thomson never made mention of anything nucleus. But by his alpha scattering experiment, he was able to propose a presence of the central core, which is the nucleus. So that is the first strength of his model. Two, Anita, by his experiment, can you tell us some of the strength of his model? Alitia, Nana Kumi, you also here. Ablina, you also here. Ashma, Blessing, please, Ernest, let the ladies also contribute. They've been silent so much today. We've gone through his experiment. Let's talk about the strength of his model. Yes, ladies, I'm waiting for you. Yasmin has shared with us the fact that he was able to propose the presence of the nucleus by his experiments. Yes, that is true as a strength. 2. Okay, Ernest.
So able to explain the scattering of atoms or subatoms.
Come again.
He was able to explain the scattering. He accounted for that.
Yes, he explained the scattering, but what conclusion did he draw? That's my question. So he proposed the presence of the nucleus, the charge of the nucleus, and the mass of the nucleus as well. Don't forget, by the fact that 1 out of 20,000 alpha particles were deflected back, indicate that there is something at the center which could deflect alpha particles back. By the deflection, he was able to tell that this thing at the center must have a charge same as the charge of the alpha particle. That's how come we are saying that the nucleus is positively charged, and then the fact that that thing can deflect alpha particle means that it must have a greater mass than the mass of the alpha particle. Okay, so what are the other observations or strengths he drew from his experiment? 2, he was also able to tell that yes, there is electrons hovering around, hovering within the hollow space or around the nucleus by his experiment. Okay, that if 1 out of 2,000 alpha particles were deflected at wider angle, then it means there must be something which is around the nucleus or within the hollow space, which actually accounted for the deflection of the alpha particle, and that is the nucleus. That is the presence of the nucleus within the hollow space. All right, so these are some of the strength of Rutherford's model. Let's look at some of the weaknesses. 1, Rutherford did not explain the planetary model of the atom. He could not propose or explain the planetary model of the atom. You see, modern day, we perceive an atom to look like the planet where we have the nucleus and then the electrons orbiting within the shells. Okay, so the present day model of the atom, the planetary model, was not seen or was not proposed by Rutherford. Okay, so he could not propose a planetary model of the atom. 2, he could not also explain the stability of the atom. Rutherford could not explain the stability of the atom. Could not explain the stability of the atom. Frank?
Please, can you explain what you mean by stability of the atom?
We'll go deeper. We'll go deeper. Before, physicists had a view that an atom will not be stable, in that electrons orbiting around You see, we have electrons within the space. So supposing this is the nucleus. The nucleus, we have electrons here within the space. Electrons would orbit, move around this, and then spirally crush the nucleus to break it down. Okay, so whilst they orbit, electrons orbit, they will lose energy and spirally crash with the nucleus to collapse or break down the whole atom. That was the classical physicist point of view of. So in that, an atom will not be stable because whilst electrons orbit, they will lose energy and crash the nucleus and then cause the collapse of the whole atom. This is the instability. So we later saw that no, orbiting electrons will not lose energy and then crash the nucleus. Okay, and that explains the stability. So an atom would always be stable because this will not happen. And it wasn't, this stability thing was not said by Rutherford. It was said by Bohr, Niels Bohr's postulate or model of the atom. So atom stability was not proposed by Rutherford. Neither was it also proposed by Ernest Thomson. So it becomes a weakness. Okay. Now note that everything that was observed or proposed by Rutherford becomes a weakness to Thomson. So all the observations or conclusions drawn by or strength of Rutherford's model becomes a weakness to Thomson. Please, are you with me? Hello?
Yes, sir. So does he also work vice versa?
Come again.
So does he also work interchangeably?
No, you see, as for the strength, because Thomson was the first possible model, yes, he helped us make some observations. But all his weaknesses were the observations made by Rutherford. When we go to the next model, which is Bohr's model, you see the strength of Bohr's model and also the weaknesses as well. So we'll discuss, we'll go deeper into Niels Bohr's model of the atom on Thursday. Then we look at the strength and weaknesses of Bohr's model as well. So these are the three main models of the atom. As disciples of physics, you must understand and know. Please, is there any question? If you have any question, quickly ask because our time is up. All right. I guess silence means no question. So we'll draw the curtains on our meeting, okay, and then continue on Thursday. May the good Lord be with you. Please, Anita, Augustine, Ernest, and Co. remind me to go through the teacher appraisal with you on Thursday. Is that okay?
Yes, please.
All of you, please remind me to do that on Thursday. Gideon.
Also, please, it's okay.
All right. So, bye-bye. I'll see you on Thursday.
Bye, sir.
All right.
Yo, don't worry.